Okay, guys, we're back at it. Our goal today is to set up kind of a hypothetical calculation in which we find the molar mass of the gas that is inside of just a typical lighter that you might buy at the grocery store or that you might buy at a gas station. And the gas inside of that lighter is known as butane. And in our last video, we said if we wanted to find that molar mass experimentally without the use of a periodic table, all we have to do is fill in the components that make up the molar mass gas equation, which is just a derivation of the ideal gas law. And so, what that leads us with is a pretty simple request that we find four things that we find out how much of the gas did we use, what was the temperature of that gas, what was the pressure of that gas, and what was the volume. And so we're going to kind of use made up numbers in this particular example. We're not doing the experiment ourselves. But it's actually a bit more complicated than you would think for something that you only need to find four things for. So we're going to talk through each one of them at a time. The first one is how do you even go about measuring any of these things? Well, before we write down a number with mass, let's talk about how you would get the mass in the first place. We want to measure grams, right? And how do you do that? Well, you measure grams or the mass on a balance. And so one way that we can measure the mass of the gas that we use that came from our butane lighter is we could measure the mass of the lighter before we started the experiment and the mass of the lighter after you do the experiment. So I've done this experiment many, many times. And typically in this experiment, here's what we've found in our classes is that you actually only use a small amount of the gas for the entire experiment. And in a typical class, here's what we've done. We have found that we used about zero point 0.1 grams. It's really right around 0.12 grams of butane gas. Okay, so easy enough to find that. But finding some of the other things are a little bit trickier, like where should we put that gas? How should we collect it, etc. And that complicates things a little bit. So I want to tell you about an experimental technique that we typically will use in the lab when we try to collect a gas. So we're trying to release that gas into a container that will allow us to measure its temperature, its pressure, its volume, etc. Well, the number one way that you do that experimentally is through something called collecting a gas over water. And this picture is not perfect because obviously it doesn't show our butane lighter or anything like that. But here's what I want you to imagine. Imagine that this setup right here is our lighter, and we are connecting it to a typical instrument from the lab, like a graduated cylinder. And graduated cylinders are used to measure volume. And all we're going to do is we're going to place our graduated cylinder into a tank of water, and we're going to fill the graduated cylinder completely up with with water. And afterwards, we're going to place our lighter underneath, kind of like this tube is right here. We're going to place uh, that butane lighter underneath the graduated cylinder, and we're going to start bubbling gas into it. And what you see right here, which looks like air to us, is really where all that butane is going to go. Okay. And it's going to start to push water out of the container. The water starts to move out of the container or out of the graduated cylinder until you collect a specific amount. Now, typically in our classes, we're working with a 50 milliliter graduated cylinder. And so once we've collected enough of the gas that we get it to exactly 50 milliliters, that's typically where we're going to stop. Okay. And so we're going to go back to the things we need to know to do this sort of problem. And we're going to put in 50 milliliters as our volume. But you know that anytime you're using the R gas constant in a molar mass equation, you can't use milliliters. You've got to have liters instead. And so we can divide milliliters by 1,000 to change it to liters, or we can move the decimal 3 places to the left, and that will accomplish the same thing. And so we're going to assume our volume is 0.0500 liters. So we filled up our graduated cylinder all the way and it's complete. Okay. Here's the other thing that is pretty easy to measure. If you collect all of that gas over the water, what we tend to find is that the temperature of the gas becomes equal to the water temperature. So if we took a thermometer and we measured the temperature of that water, we would know also the temperature of the gas. Typically, the water temperature is room temperature. And so a pretty good guess on a room temperature is around 21 degrees Celsius. So we're going to assume for this problem that our temperature is 21 degrees Celsius, but we also know we can't leave temperatures in Celsius. And so we're going to change that to Kelvin by adding 273 and we get 293 Kelvin. The trickiest thing for students to get is to measure the pressure. And so we have to introduce kind of a third law in order to do that, or really a second law for today. And it's called Dalton's law of partial pressure. Here's what is kind of tricky about this particular pressure measurement. The first thing I want to tell you is that the pressure inside of this tube, so let's call it the inside pressure, is equal to the pressure that's outside of the tube. It's equal to the atmospheric pressure. And the way that I know that is that the gas is pushing down on the water just as much as the atmosphere is pushing down on the water. In other words, if the line inside of the tube is the same as the water line outside of the tube, those two things are the same. So let's say that today we measure the atmospheric pressure, and the atmospheric pressure is 745 millimeters of mercury. That's typical for the Marist classroom. The atmospheric pressure is 745 millimeters of mercury. Well, there's another issue that poses a problem to us. We collected in the experiment butane gas, right? So we know we have a lot of butane gas that is inside of this tube. But there's something else in there that you may not be aware of, and it's not air. There's also what we call water vapor inside of the tube. So it's water in the gas form, and that water in the gas form also causes pressure. And so here's how I would think about it: that the pressure inside of that tube, inside of the graduated container or cylinder, is equal to not just the pressure of the butane, but it's equal to the pressure of the butane and the pressure of the water that's inside of the tube. That pressure, which is called the water vapor pressure, can easily be found for a particular temperature. So I've got a table on this slide, and it tells me that at 21 degrees Celsius, The water vapor pressure is 18.7 millimeters of mercury. So if I go back here, I can say that the atmospheric pressure is equal to the pressure of the butane plus the pressure of the water vapor, which we said was 18.7 millimeters of mercury. So I can find the pressure of the butane just by subtracting 18.7 from the atmospheric pressure of 745. So if I say 745 minus 18.7 equals 726.3. That 726.3 is now the pressure of the butane. But we have one more issue. And that issue is that we need our pressure measurement to be in atmospheres. And so what we're going to do is we are going to convert that pressure into atmospheres using a conversion that we're already aware of. We know that there are 760 millimeters of mercury in one atmosphere. And so if I do the math on this, 726.3 divided by 760, I get 0.956 atmospheres. So let's write that down. 0.956 is our pressure in atmospheres. And if we use that information, we should be able to have kind of a rough idea of what the molar mass of butane is. Let's see how that would be done. If I go back to the equation and I start plugging in numbers that we already have, we would say molar mass is equal to 0.12 grams times 0.0821, the R constant, which is liters times atmospheres over moles times K, times the temperature of 293 K, and divided by pressure, which we found as 0.956 atmospheres, and the volume of 0.0500 liters. I want to show you something with units before we do the calculation. So with our units, look at what cancels. Atmospheres cancels with atmospheres. Liters cancels with liters. Kelvin cancels with Kelvin, and we're left with grams over moles. So if I say on my calculator 0.12 times 0.0821 times 293 divided by 0.956 divided by 0.0500, I get a molar mass of 60.4 grams per mole. Now remember, or actually it's 60.4 grams per mole. And on the previous video, we said using using the periodic table. So if I use the periodic table, the actual value or the real value is 58.14. And so that's a pretty close approximation, the difference only coming from experimental error that we might have within the process. That's pretty complicated, feels pretty complicated, but in a typical problem, you're going to find that it is very much like any of our other gas laws. So I'm about to stop this video, and what I want you to do is find in your notes this example of molar mass calculations and Try to take about 5 minutes right now to do this problem. And when you finish it, I want you to come back and I want you to watch my next video in which I will do this problem as well. And you can check your answer against mine. Okay. I'll see you next time.